Hello students, this video gives the introduction of multivariate normal distribution. The multivariate normal distribution is one of the most important distribution in the multivariate statistical analysis. Many statistical techniques such as PCA, factor analysis, uh, multivariate analysis of variance, shortly we call as MANOVA, cluster analysis, all these analysis has one basic assumption, that is the population n follows multivariate normal distribution. So this is one of the most important assumption for all these techniques. So therefore studying the multivariate normal distribution is one of the most important thing to know the basic formula to derive or to construct these methods. So in many real world situations, measurements such as suppose if we collected data, measurements are considering as a height of a student. Okay, if it is the height of a height or weight, blood pressure, or suppose if we think the test score of students. And biological characteristics. Biological characteristics are approximately normally distributed. Okay, so we cannot able to expect that always the data set will follow the normal distribution. So it may be sometimes it may be the data set may not follow the normal distribution. In such a cases, we have to consider the suitable transformations, such as logarithmic transformation, or we can do the square root transformation, or box transformation. So by doing this, sometimes improves the normality of the data. Actually, in the logarithmic transformation, what we will do is we will take the log for the data, that is log 10 to the power of x. Suppose x is our variable. In the square root, we will consider the variable as square root of x, and in the box method, the formula which we use is x equal x power lambda minus 1 divided by lambda. So here lambda will be a value, any value. So the basic thing is selecting these lambda value. If lambda value is selected optimizedly, then this method will give this method, that is box plots method, will give the better result of normality of the data. So like this we can able to do it. And the next we are going to see about the multivariate data. Multivariate data. Multivariate statistical analysis deals with data with several characteristics or measured on each individual or experimental unit. So univariate techniques will have only one variable, say x, but under the multivariate variables we will have several characteristics, say x1 comma x2 comma etc. Suppose if it is p variables, then it is p. Okay, so therefore several variables will be considered in multivariate, rather than in univariate we will consider only one variable at a time. So examples we can say as for example, suppose imagine a production process, a production process. So in the production process, what are the variables we will use is first one is the raw material to produce that product. That is most important. And processing time, how much time it takes to produce the product. And number of defects found in the produced product. All such things will be considered as the measurements or characteristics under the production process. Similarly, suppose imagine in the educational. Okay, so educational data, suppose if we consider the educational data, in this so we think we can consider as the marks in different subjects. Okay, marks in mathematics or statistics, or it may be a physics, chemistry, etc. Suppose if a student writes or studies the different subjects, and if we collect all the data, then we can able to see that as under multivariate data type. Suppose if you take another example under economical data. So economical data. So population in that particular area can be considered population. Second, we can see as per capita income of the state or the area, or employment rate of a particular area. All such things will come under the economic data. Since several variables are measured simultaneously, so in all these examples which we have seen, we have taken several variables, and all these variables are studied in simultaneously. The observations are called as multivariate observations. Multivariate observations. So multivariate data means we will collect more number of variables and work it on in the simultaneously, then that will be considered as a multivariate data set. Okay, now we can see how to represent all these observations, because the mathematical representation of an observation is the most important to do the mathematical operations. So mathematical representation of an observations. To perform mathematical operations, we represent all measurements as a single individual as a column vector. If we measure three different characteristics, For example, as I said earlier, in the economic data, we have considered the things like unemployment, population, per capita income. Okay, so there we consider three variables. Therefore, P is equal to 3. So P different characteristics. So this is called as the characteristics. The observations of for one individual is denoted by vector X. So this is represented as like this, that is X1, X2, etc. XP, where P the dimension of the vector, so that is the number of variables which you have collected, and Xi is the ith characteristics or variable. For example, if we consider I is equal to 2, then it is X2. Geometric interpretation is each vector X is viewed as a single point in the p-dimensional Euclidean space. So this is the way to represent the observations in mathematics. So now we can see the data matrix. The data matrix. So representing the shape of the data. When we collect data from n different individuals. For example, suppose if you consider the example stated above of educational, in that if the students, if we collect for student of 25, then n is equal to 25. Okay, so number of variables which you have collected, there is mathematics, statistics, physics, and chemistry. Therefore, p is equal to 4. So like that, we can able to see the variable is 4 variables and number of students is n. So this is the representation as n and p variables. So this how we can able to put it as in the data matrix. If we organize these column vectors into a data matrix, the theoretical multivariate analysis, the matrix is typically P cross n, that is P vector, that is variables, and n observations. So this can be represented as X, X11, X12, X13, etc. Xn1, X21, X22, X23, etc. X2n. Similarly, X, if it is a P variables, then P1, Xp2, Xp3, etc. Xpn. So the order will be as P cross n. Each column represent the individual or objects. So this column, okay. So each column will be considered as variables, and each row represent all measurements of single variable across the samples. The key statistical measures. Okay, by using this data matrix, what are the key statistical measures which we can able to compute? Means actually this is the extension of univariate mean and variance. So this we will call as the mean vector, mean vector. So it is represented as mu. The average of all observations represents the center of data cloud in p-dimensional space. So this mu is expectation of x. So this can be written as so x here, how we have written? We have written as x1, x2, x3, etc., xp. So therefore, taking expectation of each variable, that is expectation of x1, expectation of x2, etc., expectation of xp is equal to this. We can able to write it as in a single vector, that is a mu1, mu2, etc., mu. So this is the mean vector. So next, the variance and the covariance matrix. Variance and covariance matrix. Actually, it is represented as capital sigma. So variance and covariance matrix plays the major role in computation of all multivariate data. Okay. So this is P cross P cross P square matrix. So variance covariance matrix will be as P cross P. Since we have taken P variables, therefore P cross P matrix that describe the spread and the relationships. So how we will write it? That is a variance of capital X is equal to expectation of X minus expectation of X the whole square. So this can be, again you can able to write it as expectation of X. Expectation of X is nothing but mu, that is mean value of whole square. So here we are writing x minus mu the whole square. So this can be written as expectation of x minus mu into x minus mu dash. Okay, so like this we can able to represent. So this can be considered as expectation of. So since x minus mu, how many variables we have taken? We have taken p variables. Okay, therefore this will be as the vector form x1 minus mu1, x2 minus mu2, sorry mu2, etc., xp minus mu p. So this is transpose. So therefore we have to write like this, that is x1 minus mu1, x2 minus mu2, etc., xp minus mu p. So once we multiply it, okay, once we multiply it, then undertake the expectation. So this will be as like this, that is expectation, that is we are multiplying x1 minus mu1 into x1 minus mu1. Okay, so therefore we can able to write it as x1 minus mu1 the whole square. So next we are going to multiply x1 minus mu1 into x2 mu2. So this can be written as expectation of x1 minus mu1 into x2 minus mu2. So similarly, we can able to write expectation of x1 minus mu1 into xp minus mu p. Okay. So next we consider the x2. So therefore we can write it like this, that is expectation of x2 minus mu2, okay, into x1 minus mu1. Similarly, it will be as expectation of x2 minus mu2 the whole square, extension expectation of x2 minus mu2 into xp minus mu2. And expanding it, we will get it as like this. For the pth variable, it will be as a xp minus mu p into x1 minus mu1, and expectation of xp minus mu p into x1 minus mu1, sorry, x2 minus mu2, etc. Expectation of xp minus mu p the whole square. So on seeing this, we can able to understand how we have getting the variance part. So now variance of x is equal to, its notation is capital sigma, is can be written like this, that is first one as sigma x1 square, and the second one as covariance of x1 x2, etc. Covariance of x1 xp. Similarly, second row will be as covariance of x2 x1 sigma x2 square, etc. Covariance of x2 xp, and we can write it as covariance of xp x1, covariance of xp x2, and this will be a sigma xp t square. So therefore variance, we will get it as like this, that is sigma 1 1, sigma 1 2, etc. sigma 1 n, sigma 2 1, sigma 2 2, etc. sigma 2 n, etc. sigma p1, sigma p2, etc. sigma pn. The diagonal elements. So this is the diagonal elements, or sigma ii will be considered as the variance part. Okay, so variance part, and off diagonal elements, that is sigma ij. Okay, this will be considered as the covariance, the covariance between variable I and j. So now we can see the basic properties of variance covariance matrix. The first and the foremost property is the property 1. Property 1, square matrix. The covariance matrix always has the order P cross P. Therefore, it is always a square matrix. So this is very simple. Second property, property 2 is symmetric. Symmetric matrix. So the variance covariance matrix is a symmetric matrix. Since covariance of xi comma xj is equal to covariance of xj comma xi. So we have sigma equal to sigma transpose. Hence, the covariance matrix is symmetric. The property, the third property of variance covariance is non-negative diagonal elements. Diagonal elements. Since variance cannot be negative. Why? Because it is a sigma square. We are squaring it. So if we square, then we will not get any negative. That is variance of xi greater than or equal to 0 always. So therefore, the diagonal element satisfies this. That is sigma square greater than or equal to 0. Therefore, it is a non-negative diagonal elements. Property 4. Property 4. So one of the most important, that is positive semi defined. Positive semi definite. A matrix sigma is called positive semi defined that is the basic definition is a matrix sigma is called positive semi definite if A transpose sigma A is greater than or equal to 0 for every non-zero vector A. Why does covariance matrix satisfies this? So let us prove that. That is A transpose sigma A is equal to variance of A transpose X. Since variance we have seen in the last property, that is variance can never be negative. Okay, never be negative. Therefore, we can write it as variance of A transpose X is greater than or equal to 0. So therefore, A transpose capital sigma A is also greater than or equal to 0. So now let us prove that is A transpose sigma A is equal to variance of A transpose step by step. In step 1, first we can define random vector. So define random vector. So X we consider as X1, X2, etc. XP, and with mean vector mu is equal to expectation of X is equal to mu1, mu2, etc. mu p. So therefore covariance matrix is capital sigma is the notation, is the expectation of X minus mu into X minus mu dash is transpose. Step 2, so now we can define a linear combination. So linear combination, take any constant vector. Okay, so now we are taking a constant vector, say A is A1, A2, etc. AP. Okay, so this is the constant vector, and here we are considering, so consider Y is equal to A transpose of X. So if we expand it, okay, so what is X? X is X1, X2, X3, XP, and what is A? A1, A2, AP. So when we multiply these two things, X and A transpose, so here the A is transposed, okay. So therefore we will get it as we will have it is as A1, A2, etc. AP, and X will be as X1, X2, etc. XP. So when we multiply these, we will get it as Y is equal to A1 X1 plus A2 X2 plus etc. AP XP. So this is the linear transformation. So combination of linear. This is the linear combination of the variables. So in the next step, what we are going to do is we are going to identify the mean of these linear transformed. So therefore, step 3. So find the mean vector. Sorry, mean of the variable y. So variable y is the combination of linear transpose, that is y a transpose of x. So using expectations. So therefore, expectation of y is equal to expectation of a transpose y. Okay. So since a is a constant value, because we have considered earlier, so a is a constant value, we can write it this as a transpose expectation of y. So here expectation of x. Okay, so we have seen expectation of x is nothing but mu. Similarly, expectation of y is also will be x, right? Okay, x. So expectation of x equal to mu. So therefore, we can write it like this. That is a transpose of mu is nothing but expectation of y. So this is the mean value. So now in the step 4, write the variance formula. Okay, so the variance. So we now find the variance for the variable y. So variance of y is equal to expectation of y minus expectation of y square. Okay. So now substitute y is equal to a transpose of x here. Then variance of a transpose x equal to expectation of a transpose x minus a transpose x the whole square. Okay. So we'll factor out a transpose t is equal to this will be as expectation of a transpose x minus mu the whole square. Okay. So therefore, variance of y. So variance of y will be as expectation of a transpose x minus mu the uh, whole square. Okay. So now we have to convert this square into matrix form. So now we are going to convert this square into the matrix form. This is the step 5. So step 5, step 5. So converting the square into matrix form. Okay. So A transpose of x minus mu is a scalar, that is A into 1 cross 1 quantity. Okay. For any scalar, yes, s square can be written as s into s. Hence, A transpose x minus mu the whole square can be written as like this. Okay, A transpose x minus mu and A transpose X minus mu. Okay. So like this we can able to write it. So now we are going to use transport to this. Okay, so this part. Okay, for in this part we are going to use transpose. That is, if we use transpose, that is A transpose X minus mu. Okay, so now consider this as a single variable and this is as another variable. Therefore, we can write it like this. This as that is X minus mu dash and A. Okay, so we know that AB dash can be written as B dash A dash. So therefore, here we are writing as, so this is the A and this is B. If we consider, then we can write it as like this. Okay, so A dash B. So this will be as our this, since it's a transpose, it will be as A transpose equal to of transpose is equal to A, and X minus mu transpose is, okay, if we transpose this will be as X minus mu. Therefore, we are getting as X minus mu dash A. So therefore A transpose X minus mu whole square is equal to A transpose X minus mu transpose A. Okay, we are substituting here. So this one, in this place we have substituted this, which we have transformed. So rearranging this, what we will get, it is A transpose X minus mu transpose A. So thus variance of A transpose X is nothing but expectation of A transpose X minus mu transpose of A. So this is the variance of A transpose X. So next step, what we are going to do is we are going to take a constant outside. Okay. So the constant is A transpose and A. So we are going to take it outside. So step 6. So step 6, taking constant outside expectation. So since A is a constant, so like that only we have considered the vector as a constant. So therefore, this can be written as A transpose. We can take it outside expectation of X minus mu transpose of A. So, but so this one, okay, that is expectation of this is nothing but capital sigma. Therefore, variance of A transpose X is equal to A transpose capital sigma, that is variance covariance matrix, into A. So hence we getting the variance of A transpose of X as A transpose and variance covariance matrix and A. So let us now prove this using numerical verification. Okay, so numerical verification. So let consider A is equal to 2 and 1. Okay, and capital sigma is equal to 2 cross 2 matrix. Okay, 4, 2, 2, and 9. Okay, and what will be the sigma A? So sigma A will be as, that is this part. Okay, so this part we are multiplying sigma and A. Sigma, okay, so this part will be as 4, 2, 2, 9 into 2, 1. Okay, so the output will be as 10 and 13. If you multiply these both the things, then we will get it as 10. Okay, that is 8 into 2 is, sorry, 4 into 2 is 8, and 2 into 1 is 2. So 8 plus 2 is 10. Similarly, 2 cross 2 is 4, and 4 plus 9 is 13. So now A transpose sigma A is equal to, so now we got this value. Okay, so this value as 10, 13, and we are going to multiply that with the transpose, A transpose. So the A transpose can be written like this, that is 2, 1, and the sigma A is 10, 13. So this we will get it as 20 plus 13 is equal to 33. So the variance of this matrix is a single value, that is 33. Okay, so the numerical value which we obtained, that is of A transpose sigma A, is 33. Now compute directly using variance formula. So this thing we have written in A transpose form. So now whether the variable, that is the original formula which we are used for computation of variance, using that, if we use, whether we get the same answer or not, we are going to consider. So now we are going to compute directly. Okay, so directly using the variance formula, the variance formula. So y will be as, since A is considered as 2 cross, so 2 and 1 into, we are multiplying as x1 x2, so therefore it will be as 2x1 plus x2. Okay, so the variance of y will be as 2 square variance of x1 plus 1 square variance of x2 plus covariance. Okay, 2 cross 2 into 1 covariance of x1 x2. So this will be the variance. So here in what way we have written is expectation value. Okay, so this will be as a variance of x1. Okay, so the variance, so variance of x1 is 4. Okay, so that is sigma values we have taken. Variance of x2 is 9, and covariance of x1 x2 is equal to Okay, so covariance is a symmetric, therefore x2 and x1 is also 2. Okay, so therefore we are getting as like this, that is 2 square is 4 into variance is 4 plus 1 into 9 plus 2 into 2 4, 4 into 1 1. So therefore 4 into covariance is 2. So therefore 16 plus 9 plus 8 is equal to 83. So therefore variance of 2x1 plus x2 is equal to A transpose sigma of A, that is 33. So the numerical result confirms the proof. Okay. So the most important interpretation of A transpose sigma A. Actually, this A transpose sigma A is not an just matrix expressions. Okay. So that is A transpose sigma A is not just a matrix expression. It is the variance of linear combination. Okay, so this is variance of linear combination, that is a1 x1 plus a2 x2 etc ap x2, and we have seen earlier that is variance cannot be a negative, cannot be negative. So therefore A transpose sigma A will be greater than or equal to 0. So this single result is the fundamental reason why every covariance matrix is positive semi definite. Okay, so special cases are there. Special case, if no variable, okay, if no variable is an exact linear combination of the others, comma, then A transpose sigma A is greater than 0 for all non-zero vector A. In that case, okay, in that case, sigma, that is variance covariance matrix, is positive definite. So the basic difference between positive definite and positive semi-definite is greater than and equal to. Here it is only greater than. 0 is not considered. Okay, if 0 is not considered, then it is called as positive definite. When it is greater than, that is positive, and 0 is included, then that is called as positively semi definite. Okay, so the basic thing, one of the most important thing while we are deriving the multivariate normal distribution, we will take the matrix as a positively defined matrix, then only we can able to prove it. Okay, so therefore this proof is the most important thing for considering the derivation part of probability density function of multivariate. Okay, in the next video we can derive the probability density function of multivariate normal distribution.